All right, so now we're going to talk about projection methods, which are a particularly simple way of developing numerical methods which preserve first integrals. Okay. So this is a straightforward means of constructing methods that preserve a given first integral. Is by this method of projection. Okay, so let's consider a vector and a hyperplane. All right, so let's consider a vector. Say u in Rd. Okay, and a hyperplane P. I'm sorry, okay, defined by sort of a orthogonality condition that s dot y is equal to 0. All right, so how might you go about sort of defining a projection method? It's like given this, so we can project u, right, onto such a hyperplane. By introducing a Lagrange multiplier. Okay. So let's sort of think about exactly what's going on here. So, okay, so you have this normal, it's like to the plane, it's like which is s. Okay, so let's imagine this is the direction s. Okay, and then you've defined it's like a hyperplane P with the condition that you have y with the property that, and this is of course the origin, right? And you have the property that it's like every point, it's like y, it's like on P is orthogonal to this vector s. Okay. All right. So and then what happens is that you have another vector u, which you would like to project, if you will, it's like onto this plane P. Okay. So, and so what you do is that you have y, right, which is going to be u plus some multiple of this normal vector s, okay, and this multiple is denoted by lambda, which is a Lagrange multiplier. Okay. All right, so what that means then is that you have this u direction and you allow yourself to move along this normal direction in order to achieve the condition which defines the hyperplane. So what you do then is that you have this is the given a point u, you like to find a projection of this, which I denote by y, onto the hyperplane P. And of course, it's like you want to impose the condition that y is on the hyperplane, which is this s dot y condition. So you have this 0 is equal to s dot y. Okay, so you have a system like this. So you can then easily solve this, right? So from this, and the way, of course, you solve this is you take this y expression, you substitute it into the defining equation, and then what that allows you to do is to get an expression for lambda. So you can eliminate this Lagrange multiplier. So from this, we obtain the following, that 0 is equal to s dot y, which is u plus lambda s, right? So this is just lambda s dot s plus s dot u. Okay, so that means that lambda is equal to minus s dot u divided by the norm of s squared. Okay, and then you can substitute this back into the expression for y, so that tells you that y is equal to u plus, well, minus s dot u over s squared times s. Okay, so so of course it's like one way to interpret this is that I can rewrite this term here in the following way. I can write this as s dot u divided by the norm of s times s over the norm of s. And so I can think of the unit vector, it's like in the direction s, which I denote by s hat, right? S hat is s divided by the norm of s, right? It's the unit vector, again, in the s hat direction. So when you do that, this expression then becomes s hat dot u, right, times s hat. Okay, so of course this is nothing more than saying that you take this u vector and you take the component of it, the magnitude of the component of it in this s direction, right? This is what s hat dot u is, and then you look at the vector, it's like associated with that. Okay, so this is the projection, if you will, and then you just shift it down by that amount so that you end up on this hyperplane P, right? So that's basically what is happening here. Okay, so that's perhaps not so surprising, and there's a nice interpretation of that. Okay, so so here, of course, we've assumed that s is not equal to 0. Right, so where we assumed that s is not equal to 0. Okay, so y then is the orthogonal projection onto the hyperplane. Okay, so so of course it's like what oftentimes happens is that your constraint set is not a hyperplane, but then you can ask, well, can we look at a the level set of say a scalar valued function which corresponds to some sort of codimension 1 hypersurface. Okay, so this can be generalized from a hyperplane to a manifold of codimension 1. Say satisfying the condition that it's the level set maybe of say the 0 level set of some integral function, right? First integral function, say I of y is equal to 0. Okay, so what is meant by something having codimension 1 is that if you have an ambient space of dimension d, it's like then this manifold of codimension 1 has dimension d minus 1. Okay. All right, so now we want to look at the 0 level set of maybe some first integral. Okay. All right, then what happens is that instead of this set of equations, the set of equations you want to have is the following, right? Then you solve the following. Nonlinear equation now, nonlinear system. which says that you again that y is equal to u plus lambda times, instead of s now, you replace this with something which is, so if you imagine this hyperplane, this, not hyperplane, but sort of this codimension 1 manifold, which is the 0 level set of I of y, right? So this I of y is equal to 0. Then you want something which plays the role of the normal. It's like to the hyperplane. So the normal of this is just given by the gradient respect to y of the sort of first integral. Okay. So instead of s here, you replace this with the gradient of I. Okay. So you have gradient of I. And then again, instead of the condition that you know, it's like s dot y is equal to 0, you replace it with the condition that you're on this you know, codimension 1 manifold, which you want, which is defined by the condition I of y is equal to 0. So I write 0 is equal to I of y. Okay, so this is sort of the nonlinear analog, if you will. It's like of this simple orthogonal projection formula, which you know. All right. So let's see what you can do with this. Okay. So, right. So one way to think about this is that this corresponds to some sort of constrained, you know, L2 minimization. So this corresponds to the sort of L2 constrained minimizer. Right, in the following sense, that y is equal to the arg minimizer over things which are on the constraint set of the L2 error between u and y. Okay, so this projection is orthogonal in the following sense. So let's draw a picture for you, just to give you a sense as to what we mean by saying that this is the analog of an orthogonal projection. Okay, so if you imagine that you have some function, all right, I of y, then if you have a point u here, right, then this y has the property that if you look at the sort of the defect, if you will, the difference between u and y, then this is sort of perpendicular. It's like to the tangent, if you will. So you have the gradient of I of y here. Okay, so this is a sense in which you know, you have a projection. It's like this nonlinear projection, which is orthogonal in some sense. Okay, so more generally, right? So more generally, if B is any vector such that S dot B is not equal. So I'm going back now to the hyperspace, so hyperplane case just for a bit. It's like, and then we'll go back to what it means in this nonlinear setting. Okay, so I should say back to hyperplane case. Right. right? So if instead of choosing, it's like this sort of normal to the hyperplane, more or less you need to just have something which is transversal to the hyperplane, right? So it's more or less just not in the direction of the hyperplane. So if b is any vector such that s dot b is not equal to 0, right, we can solve the hyperplane equation. Projection problem in the following way. By solving for y and lambda such that, right, y is equal to u plus lambda b, and then 0 is equal to s dot y. So instead of moving this in this normal direction to the hyperplane, you can move in anything which is transversal to the hyperplane. And of course, you don't get now a orthogonal projection, but you get what is called an oblique projection. Okay, so this is referred as an oblique projection. And then for nonlinear manifolds, what you have is very similar, right? So y is equal to u plus lambda b as before, and then the only thing which changes is you replace the defining equation for the hyperplane with the defining equation for your nonlinear manifold, which is that 0 is equal to I of y. All right, so and again, all you're doing then is that if this is the level set I of y is equal to 0, right, then you have a point u, you have a direction vector b, right, and then you have just some point y, which is on the manifold and which is along, you know, the ray, it's like, which is generated by b, it's like starting from u, right? Okay, so let me just stop here for a minute, and then we'll talk about the numerical case.